Hello, statisticians, and welcome to section 9.5 Excel tips on hypothesis tests for standard deviations. When we're working with a hypothesis test claim about a standard deviation or a variance, we use a different distribution called chi-squared. So on Excel, we will use equals chi-sq dot dist, open a parentheses, our test statistic, comma, the degrees of freedom, which is the sample size minus 1, comma, true. That'll give us the left tail of the chi-squared distribution. If we want a right-tailed test, we'll use .rt and we no longer need the true argument. If it's a two-tailed test, we'll take the smaller one of the two and double it. In order to find that test statistic, to use the command to find the p-value, we first need to use the formula for chi-squared, which comes out of your textbook. Let's look at an example where we do that. We have a machine that measures 16 weights and find those 16 weights have a standard deviation of 0.8. Something to be careful of, since it's a standard deviation of a sample, that is actually the S. We want to show the standard deviation is actually less than 1.2 grams for all weights this machine makes. Because that 1.2 is representing all weights, that's going to be the Greek letter sigma. So if we want to set up our hypothesis test, our null hypothesis is that sigma is equal to 1.2, and the alternative hypothesis is that sigma is less than 1.2, because we're trying to show it's actually less. Now this hypothesis test is set up with the standard deviation, but we could have set it up with the variance as well. In that case, the null hypothesis would be sigma squared, representing the variance, is equal to, and 1.2 squared is 1.44. And the alternative hypothesis would be the variance sigma squared is less than 1.44. So depending on what's being asked for or what we're interested in, we can set up the hypothesis as a sigma, or a standard deviation, or as a sigma squared, which is a variance. When we get to calculating the chi-squared value, the formula for that is going to be n minus 1, or the degrees of freedom, times s, and because that's an English letter, that's the sample standard deviation, squared, divided by sigma, because that's a Greek letter, it's the population standard deviation, squared. Be careful to know if you're working with a standard deviation or a variance, because that does change the values. But we can figure this out for our example here by saying equals, open a parentheses, the sample size was 16, minus 1, times s, my sample standard deviation is 0.8, squared, divided by sigma, the population standard deviation from the hypothesis test is 1.2, squared. And when we hit enter, we find our chi-squared value is 6.666. Now we can use the chi-squared command to find our p-value. Before we do, we need to make sure we're in the correct tail. So a chi-squared starts at 0, goes up, and levels off. It's skewed to the right. We want to show that it is less than, which means we're over here in the left tail. So we're going to use the left tail command to help us find the p-value. We'll say equals chi-sq dot dist, open a parentheses, the chi-squared value, which we can just select, comma, the degrees of freedom, there's 16 weights, 1 less than 16 is 15, comma, true. And when we hit enter, we get a p-value of 0.03375. For this problem, let's let alpha equal 0.05. We should have known that from the beginning. Since that p-value is smaller than the alpha, our decision is going to be to reject the null hypothesis in favor of the alternative, which means we've rejected that the standard deviation is equal to 1.2. We have successfully proven that it's less than 1.2. So our interpretation puts that alternative and our success in context. There is significant evidence to conclude that the standard deviation of weights made by the machine is less than 1.2 grams. Let's try a second example that switches it up and makes it a right-tailed test, but following much the same exact idea. This time we're going to show that the standard deviation is greater than 0.5. Our null hypothesis is that sigma equals the 0.5. The alternative hypothesis is that sigma is greater than 0.5. Or we could have done it with a variance. The null hypothesis then would be sigma squared is equal to 0.5 squared is 0.25. And the alternate hypothesis is sigma squared is greater than 0.25, depending on if we want to talk about variance or standard deviation. For our chi-squared test statistic, it's the exact same formula. So we'll say equals, open a parentheses, the sample size is 16 minus 1, times S, the sample standard deviation, which of the 16 weights, it was 0.8, squared, divided by sigma, the hypothesized standard deviation of 0.5, squared. And that's going to give us a chi-squared value of 38.4. Again, if I draw a picture, chi-squared starts at 0, comes up and levels off to the right. We want to show that the sigma is greater than 0.5, which means we actually have a right tail. So we'll use the right tail chi-squared command. Equals chi-sq dot dist dot rt, open a parentheses, select our chi-squared, comma, the number of degrees of freedom is 1 less than the sample size. There were 16 weights, so 15 is the degrees of freedom. And when I hit enter, we find our p-value is 0.000787. Looks like this example didn't tell us the alpha either, like it should have. Let's say alpha again is 0.5, which means our decision with such a small p-value is to reject the null hypothesis. Our interpretation then, we successfully showed the alternative, so there is significant evidence to conclude that the standard deviation of weights made by the machine is greater than 0.05. Oops, 0.5. There we go, 0.5. Hopefully this helped you do the chi-squared distribution on Excel. Good luck to you, and we'll see you on the next video.